Shouldn't this be negative J? Because one over. Well, according to Wikipedia. But that's what I ended up getting. So my J turned into minus J. But I didn't either. I was should have known from work earlier. I'll one day learn my properties.
Okay, homework here, please.
I did it last night. And I thought to myself,
Sure.
Should I grab these? And here are my solutions.
he's like, nah, I'm all good.
John Wellman? That's a bit of And here's assignment number 9. It includes a homework problem G17, which I'll hand out in a moment. And I'll talk a little bit about it.
No, I did it wrong.
I did it wrong.
And lastly, on this pink sheet, I talked with Professor Sebo, and we agreed on Friday, this coming Friday, the 19th. We're not going to meet here, we're going to meet in the high voltage laboratory, right? And then for about, we figure about 20, 25 minutes, we'll give a little demo of the high voltage lab, and then we'll come back up here, all right? And so I have this pink sheet, and if you don't know where the high voltage lab is, it's down in the basement. And if you take the stairs, that's one way. If you take the elevators, another way. But anyway, I have a little map to guide you down there so you don't get lost, which you will, I'm sure. Okay, so we'll meet down there. And then he will take care of it for 20 minutes, and then we'll come back here. All right? Okay. Let me say a few words about G17. We are now, where are we? We are at the point where, using Mr. Beal and Mr. Savart's fancy-dancy integral law with that cross product in it, we can get the tensing up of the universe due to the current that is in that integral, right? I call that circuit number 1, giving rise to B sub 1 everywhere in the universe. And in order to get that B wherever you want to, doesn't matter where you want, any place, you have to do that damn integral. And then before I continue in that stream, let me say, then there was a second step. In order to detect that guy, you could put a North Pole there. But what the hell is a North Pole anyway? First of all, a North Pole doesn't exist by itself. It has a South Pole, so it might not be the best detector, although that's the detector that the Beal and Savart people used, actually, a compass needle. But then I said, oh, this guy Ampere came around and said, no, you don't have to use as your detector a permanent magnet. You can use another electric circuit. And so there's another circuit, C2, carrying a current I2, giving rise to a force F2 on that circuit. Of course, if you're not interested in the force on that circuit, but you're interested in the force on the C1 circuit, they are the negatives, one of the other. Just very similar to the electrostatic world. All right? You got that? Except the electrostatic world, it was kind of easier because you just put a charge there and you get a force on it. And then that force is the negative of the force on the mother charge and all that business. But conceptually, it's the same thing. It's just that we're not talking about charges to charges, but currents to currents, okay? That's kind of where we were. Do I have to write it all on the board? I hope not. Those fancy integrals, two integrals actually, 1 over C1 to get the B, 1 over C2 of the current in the second circuit crossed into that damn B that you got from the first integral. And so you got two integrals, 1 over C1, 1 over C2. And that's the way you do it. You do first get the damn B from the first integral, B sub arts integral, and then you do the second integral over the second circuit, the detector circuit. Got it? Now, the point that I want to make in this 17 and in this course forevermore is that I do not want you to, I want you to do some of the examples or read some of the examples that I give in my notes of using Biot-Savart to go get the B field of a shape of some sort. And I give you a bunch of shapes. A straight line and on the bisector, a straight line and off the bisector, a circle and on the axis. I do the Biot-Savarts and I get the B fields in those special cases, all right? I do it for you. Now the point is that when we get the result, let's say of a circle and the B field on the axis of the circle, whether it's high above the circle or right in the center of the circle or below the circle, I don't care. We got the answer. And I want you to use that answer. So as I pointed out, maybe if I give you a circuit of current flowing around something like that, and I want the B field right here, I can find what the B field is to the side, off the end of a finite length of current. That's one of the examples that I give on page 192A and B. I mean, it's a library of shapes. In this particular case, a shape of a current going from here to here, maybe L long or however you want to denote it, and off to the side by a distance rho or however you want to call it. And I tell you what that B field is due to that. Well, if it's good enough for that, it's good enough for this one. It's the same sort of thing. And how about this one? Well, he's on the bisector. I give you in the library, what's the B field off the bisector of the length of current so long? So you got a 1, a 2, a 3, B1, B2, B3, and you get the B field right there. Then I also give you the B field of a circle right in the middle. Well, we don't have a circle, we have a half a circle. So you take the answer for that one, divide by 2, and you got the B field of that fellow. You got that, you got that, you got that. So this is what I call the building block technique. That's a building block, that's a building block, that's a building block, and that's a building block. And you're building this weird structure from simple structures for which I have given you already the integral, the Biot-Savart integral, okay? And that's what this is about. Now, in this one, this is one again, but I give you an arc of a circle. Oh, that's not even a half, that's a quarter of a circle, and then a straight line, and I ask for the B field. What do you think? There's on the bisector, and there is in the center, not of the whole circle, but a quarter of a circle. So it's a real simple problem. If you use my results for a circle and for the bisector, I think it's number 1 and number 6 in my little library, and you get the B field over here. Now, if you want the B field in some strange place, well, a little more complicated. I'll talk about that just a tad. But I won't give you anything so complicated in the quiz, all right? I mean, so you'll be able to use the library, so to speak, and build up a real complicated mess if you want to. I'll give you another problem with a real complicated mess, but made up of all these building blocks, of which you know each one, and therefore it's the sum of them, okay? Then the last thing to remember is, that right hand. None of this left hand business. The right hand, okay? So, for example, if I had the current flowing, of course, I have to flow around. Like I can't have this one suddenly go reverse, right? So he's going like that too. Now, the question is, what direction is the B field due to this one? Put your thumb in the direction of the current. Always do this. Thumb, grab the wire, in other words. Grab the wire, and the thumb is in the direction of the current. Then the B field for that one is in. Is it not? Do the same thing for this one. This one, put the thumb in the direction of the current and it circulates around. By George, it's in also. You take this one here, do the same thing. It's in also. Take this one, it's also in. You understand what I'm saying? So that would be, in that case, the sum of a B1, B2, B3, B4. No negatives in there, all the sum. Now, if I made this like that, well, again, the current is like so. Then, essentially, this one, you put your thumb in, then it's out. So it would be this one plus this one plus this one minus that one, and stuff like that. So the right-hand rule is important to see which direction, and then if you get a result that says, oh, it's, in other words, you had B1, B2, B3 plus the B4, and you get a positive or something like that, and by the right-hand rule, it should be negative, well, then you know something's wrong. So use that right hand, okay? So that, together with the library, you should be able to solve any problem I'm going to give you in quizzes. You should be able, without doing B.O. Savart, which is a pain in the ass to do. You'll see, I mean, if you study the problems I do in my notes, going right back to B.O. Savart, you'll see, hey, it's sort of a mess there. Not hard, but a mess. And I wouldn't ask you to do such a mess in a short quiz that's 20 minutes long. Homework, maybe, but even homework, I'm not going to do that. Right? So that's what this guy is about. Now, on a quiz, I can give you more complicated ones, or maybe just as simple, but thought-provoking in another way. All right? Questions here? About that. All right. Let me say, like I said, I got about 6 cases in that library on these pages, 192, A and B. If I were you, the smart thing to do would be to tab those pages, because you're going to flip to them during a quiz. You got to flip to them. I mean, wow. So I would really tab these pages right here, so you can just flip right to them. Okay? I hate to talk about it as being plug and chug, but that's really what it is, plug and chug. But the last one, number 6, is this problem right here. Here's the z-axis, y, x-axis, and draw it heavy. This is in the plane of the floor. You've painted a circle with the center at the origin and with, let's say, radius A. And of course, here this is essentially circuit C1. This is the mother that's going to cause a B field everywhere in the universe. And we're interested in the B field on the axis. So when I say the axis, it can be here, or here at the center, or here, and so forth. And so this has a current I1, dL1, and you know the L1 is equal to the radius times the B phi in the cylindrical system and all that. That's what I do when I get the B field on the axis of this guy right here. I do the integral. Okay, now I also mentioned that, oh, hey, I got this wire that's running around on a circle of radius A, but it's got 2 turns, so it goes around again. So that would be equivalent to having 1 turn with 2 amperes instead of, in other words, 1 ampere twice, rather than 1 circle and with 2 amperes in it. So I call that N, the number of turns. That's very common, the number of turns. And the assumption is, of course, that the wire is real thin, so they're really at the same position. Now, I forgot the pages, it's after 192, I think. I do a case where there's a circle, and another one, and another one, and another one, and there's 10,000 of them. So it isn't all laying on top. That's a solenoid. Very important thing, actually. I mean, you know, like when you turn the key in your car, it's really, you don't really think that there's, let's say, 90 amperes flowing through that switch. That switch has very small current flowing through it, and what it does is it excites a solenoid, which takes a piece of iron and slams it against another contact, and that's the thing that carries the 90 amperes, all right? So you have solenoids all over your car. So that's an important guy. And when I say it takes a piece of iron and slams it, that's forces. When we get to it, when we talk about some iron, I will talk a little bit more about this. But that's another example, but it's one where you have so many turns that they can't just be on top of one another. You can't picture it this way. You have to picture it kind of like on a tube or something like that, okay? But perfect, okay. I mean, you can do that kind of stuff. But let's go back to this one here. So let's say I only got one turn, so this is just one, and then I'm back to my old self. Now, what you want to do is you want to get the B field up here at some Z, or if you want to write it as X and Y and Z, you can say, well, the X is 0 and the Y is 0 and the Z is whatever. So I'll just write it as Z. It's not off the axis, okay? Now, if you put yourself up here, and let's say you have painted this thing in the floor, and you're standing right on that axis and looking down on that circle, what do you see? You see a circle. You see a circle. Now, when you think about it, in fancy-dancy Bonnell-Kangas law, it's inversely proportional between, let's say, here's the little differential of the current. This is like I1 dL1 right here, the little guy right here, and another, and another, and another. But the point is that this rubber band from the mother source to where you want to be, as you integrate around, stays rock steady, right? Whatever this length is, it's the same as you move around. So that denominator, which goes as the inverse square in the Bonnell-Kangas, comes out of the picture, actually. It doesn't change with phi as you go around. So you take it out of the integral. That's what makes that integral so doable and beautiful, okay? You can actually do that integral, and I do it, and I get the result. I won't write it, it's in the notes. What the B field is as a function of Z. Got it? Now, let's say I go off the axis. I go over here someplace. I mean, however you want to go away from the axis. Maybe you can picture it like this, something of this sort up here. So you go around phi and then you go up a certain, so you're in some strange place out there. There's a B field over there due to mother, okay? But if you take a look, now place yourself here and take a look. So let's say the circle is over there and I'm over here now. I'm not on the axis. What do you see in the floor? An ellipse, right? You studied in your high school, you saw conic sections and all that. If you take a slice through that circle and you get off the axis, you see an ellipse. And of course, in that case, as you're integrating around here, then the distance between you and the mother varies quite a bit as you go around in phi, right? Yes, and that means that damn denominator, which is, in the way I've written it, a cube of that damn thing, the length of the rubber band, as you do the integral on phi, it turns out that that integral, well, they call it an elliptic integral because of the very fact that that looks like an ellipse. But aside from that, you can't do that integral. There is no, you can't write it in sines and cosines or any kind of complicated function. You cannot do that integral. You have to do it numerically. Got to do it numerically. And as a matter of fact, I forgot what pages, but when I talk about this circle business and this, I say, well, let's not go over here. Let's actually go in the plane of the, let's go so far off that you're like over here. So here's the case where you have the circle, and then you're in the plane of the circle, and you go a distance away from it. You can't do that integral analytically. You have to do it numerically, and I do it, and I get what the B field is as a function of going all the way from the center through the wire and out. And you'll find that it kind of goes, of course, when you get real close to the current, it's going as the inverse square. So the inverse is getting, the bottom is getting smaller and smaller, so it blows up, and then it changes sign, and it goes something like this. And then, of course, the same, I only picture it half of it like this. So it goes up to infinity, technically. Actually, there's a width maybe to the wire, so maybe not quite infinity, but it goes real high, and then it starts out like so. And again, don't forget, the B field, use the right-hand rule, so it's in here, it's out here, so that's why you have this change in sign. And then it gets weaker and weaker as you go out. Okay? But you have to do that integral numerically, and that's what I do, and that's the kind of picture I get. And if you wanted to go here, you get that sort of thing. All right? In between here, it's sort of fairly constant like that. Which is interesting because if you take, let's say there's a diameter here, some diameter to this thing, let's say 5 feet, and then you go and you make another loop, same size and 5 feet away. So in other words, the spacing between this loop and that loop, you find that the B field in a region about halfway, the half diameter, that'd be 2.5 feet, and 2.5 feet this way, is pretty constant, pretty constant. Now why might that be important? Because there's a B field in this room due to, guess who? Mother Nature's great big magnet, permanent magnet. Okay, and let's say you have an experiment where you can't have any B field, like low temperature experiments, you have to have 0 B field. So what do? You have Mother Nature. You can't. I'm not going to go. Well, even if I go to Mars, then Mars is going to have his B field. So basically, what you do is you take Mother Nature's B field from the Earth, and you cancel it with something like this. I mean, with 2 loops, diameter, space diameter, and they call that a Helmholtz coil. 2 loops of current running around, and that will cancel out over a pretty good range, big enough. Depends on the size of the loops, big enough so that maybe you can do your experiment in that space where there's no B field now, okay? Stuff like that. I mean, quite practical things. I remember when I was in college, a senior in college, our professor, like me, took us over. I went to a small school. And just across the way was a little building, and that was the physics department. They had a separate little building, beautiful little building, and they did experiments. And I remember the professor gave us some demos and stuff, and he had a Helmholtz coil. I didn't understand what it was all about at that time, but in the ceiling he had a big loop of current, and on the floor he had a big loop of current. And that was his Helmholtz coil because he was doing a low temperature experiment. He needed to have no B field right there where the circles were. Yeah, at that time, of course, I didn't know anything about that stuff, but I do remember, boy, that was strange, on the ceiling and on the floor having these wires, circular wires. Well, anyway, but now I understand it, and now you understand it too. This coil will give you a B field, and another coil will give you another B field, and it turns out to be pretty constant from half to half to about half the way here. So it's a cylinder of no B field, pretty much. Of course, you have to adjust the currents in order to cancel out just right, because the B field is dependent on I. So if you double I, you're going to double this, so you make the current just right so that it does buck, stuff like that. Then you have to use meters, magnetometers, and fancy things like that to measure the B field and say, yep, it's 0. Okay, are we there? Now, that was a step 1, and I'm trying to give you advice to don't use Biot-Savart. Don't evaluate Biot-Savart. Use my library, because the shapes I'm going to give you are included in the library. I go beyond the library and I talk about, well, if you can do a loop of current, you could do another loop of current, and another loop of current, and another loop of current, and another one. So in other words, if I have some surface current density, sort of like a whirlpooling around on this copper disc, and I want to get what the B field is, again, not off center, but along the axis, I can do that. So knowing the circle as a building block for that, I can build this one up. kind of neat. And then also, if I can do this length of wire with a current flowing on it, I guess L over 2 to minus L over 2, I can make this L over 2 infinite, and minus, I can have an infinite wire. That is really useful. I might give that a lot as far as involving problems and so forth. And you find that, by George, the B field, that is, first of all, if the current is going up, the B field is into the board. If I use my classic X and Y and Z, then this is called the phi direction. So the B field is, if you're in the plane of the board, it would be, I suppose, in the negative X direction. But more generally, it's in the phi hat direction. It is proportional to the current by 2 pi mu 0 inverse and then the distance away. Very important formula. I mean, I'll be using this. That's one of them in my library, right? This is one of the cases in my library. And actually, as I pointed out last time, it doesn't matter. I mean, it's derived from the minus L over 2 to L over 2 one, the bisector. But as this goes to infinity, there is no bisector you have to worry about. So it's good for any place you want to be along this line, so long as it's rho distance away. This formula will work. Okay, you understand what I'm saying? Okay, so we have the B field away from a hair carrying current. Well, if you can do that, you can do another hair, and another hair, and another hair, and another hair. Okay, like this. Or in other words, you can take a strip of metal and again have a current density of the surface sort, J, amperes per meter, amperes per meter, amperes per meter, 3 meters, whatever. You can do that. And for each one, you can go get yourself a B field. The closer ones would give you a little bigger B field, the further ones a little smaller. You have to do an integral across here in order to get the B field there. But you've got the basic building block of that one, which is just a hair, okay? And so you can get the current, you can get the B field of a strip, a flat strip. And then, of course, comes the question, well, what if I'm away from the strip this far away? Okay, but I'm not. How about if I'm that far away, but I'm over here? I mean, those are different. Yep, they are. You can do this one, and you can do that one. You can do this and that one, and then you say, well, what if I make this go really far away, and I make this really go far away? It's just like looking at a star. It looks like a point source, but it's a gigantic, big source of light. Well, if you go far away from this strip, which is as wide as my hand, and you go 30 miles away, what does it look like? It looks just like a little wire. So you find that the B field going this way to infinity, or to real big, winds up to being essentially the same as if you went real far away going that way. They turn out to be the same because this thing looks like really a line source now again. You understand what I'm saying? Far away. Now as you get closer, nope, they are different. And I do that in my notes. I mean, you don't have to do it. I do it. Just as an example, just a cute thing to play around with. And that really is not electromagnetics in a sense. It's just doing those integrals. It's more a math problem than it is an electromagnetic problem. So you wouldn't worry about that, would you? No. Okay. And then the last one is that solenoid business. I do that one. And again, because getting off from the axis is a problem, I get the B field only on the axis of the solenoid. So let's say if you have a long tube and you wind it up with closely wound so they're touching one another practically like that, I get the B field on the axis. And you find out that the B field is pretty constant through here, except toward the end they taper off. And you find at the end it's about half of what it is in the middle and stuff like that. You can show that. But that's only on the axis, and it's only for a very tightly wound coil, not a loosely wound helix like that, and business like that. Okay? So in other words, you can do Biot-Savart for some of these interesting cases. And then, of course, I suppose you could do, I mean, what if the coil was squashed and it wasn't a nice circular paper kind of tube that you're dealing with, but it was squashed so it was elliptical. Well, then the mathematics gets really difficult, right? I mean, then you don't learn anything new about that electromagnetics. So I don't do things like that. I suppose you could. And some of them might actually need a computer to do. Okay, but now, so that's talking enough about Biot-Savart and the tensing up of the universe called the B field of a mother source, mother current source on C1. Then there's that second step called Ampere's force law, right? Where you then took the integral around a second C2 of a second current, I2 dl2, crossed into this R2 minus R1, something like that. And then you integrate all the way around C2, excuse me, not R2 minus R1, B due to 1 evaluated at R2, something like that. And that would be the force on number 2, when you've integrated all around the circuit number 2. That's the second step. Now, in the book and in my notes, we do a special case. We say, oh, well, let's go back to our mother source, the real simple one that goes to infinity and minus infinity, right? That would be C1, and let's say this is I1 dL1. I'm now getting the B field due to an infinite line source along the z-axis, let's say. What did I say? Oh, that thing winds up to be B at any rho away. You want to call that rho, you want to call that y, I don't care, is equal to, in the phi hat direction, I1 over 2 pi u0 inverse, and then that rho, and that rho is a constant. So now, the easiest thing to do is to say, oh, I think I'll put the detector circuit be another, the C2, be another infinite guy right here, and then the rho, which you can call, I think I call it D, you put another wire, and then have a current, I can have a current going up or going down, I don't care, I2, DL2, something like that, on circuit C2. This is the detector, this is the mother. Actually, if you want to consider it, this is the mother and that's the detector, perfectly okay. But what you want to do is you want to find a force on this guy due to the B field of this guy, right? That's the idea. And I solved that problem. The book also does solve that problem. And we come up with something like the force on number 2. The force on number 2 is equal to the product I1, I2. Of course, if you double this, you double the force. If you double this, you double the force. If you double them both, then you quadruple the force. So that's all that's saying. And then divided by this 2 pi u0 inverse, and then the spacing d. And it is in which direction? I mean, you have to determine the direction. Well, that cross product is what tells you the direction. And the way to do that is to say, okay, if the current I1 is up, then what direction is the B field? Oh, it's into the board. This is the direction of the B field. And then you say, oh, I2 crossed into the B. I2 crossed into the B that you just talked about as being into the board. What is that? What direction is that? Well, the I2 is like that. If I take that and I crossed it into the thing, it's that direction. So F2 is in that. So this cross again plays a big role, and it isn't B crossed into I, it's I crossed into B. Understand that. And then of course the force on the other one is just the opposite. So that would be the F1. Okay, and equal and opposite. Do you understand what I'm saying? So you're using your right hand again to do that cross product. The first number crossed into the second one, and you get the direction of the force. Now, you take a look. That's kind of interesting. How do you remember? I mean, the way I remember it is, okay, if I got a current going this way and another one going that way, then the forces are opposite. In other words, they're trying to separate from one another. If you have a current that's, let's say, up, and this one is also up, then they're trying to come together, right? I mean, the current changes direction. So co-parallel is attractive, and anti-parallel are repulsive. And the way I remember that always is to think of the lowly lamp cord. Now, lamp cord is nice and pliable. I hope it's nice and pliable. And you know why? Because it's not a piece of solid copper. They don't make lamp cord out of solid copper. They make lamp cord out of a lot of fine things. If you know, it's all fuzzy when you cut the insulation off. You find all this fuzzy stuff out of different. That's what you're seeing here. If you take it, and the current is flowing. Current is flowing. Those are lines with co-parallel. Co-parallel. So what are these guys trying to do? They are trying to collapse. You don't find that when you plug that lamp in, that thing explodes. No, actually, although the current isn't very much, so the forces are very small, but basically it's trying to clamp down. That's what it's trying to do. And so just think of the lowly lamp cord and not blowing up in your face when you plug the thing in, your lamp into the wall plug. It's really doing this and not that, because the currents are co-parallel and not anti-parallel. Okay, and who's at work there? Mr. Ampere. That's who's at work there. Now, yeah.
Could you explain how you got the direction of the force again? Right there.
Do you know how to take cross product, A cross B?
Yes.
Let's say is equal to C. So if I have, let's say, A, and I have B, which direction is C in?
Up.
Up. Cross product. You turn one into the other, and you ask, how does a right-hand screw go? If I had a screw here, and I turned, it's A crossed into B. So A turned into B with like a screwdriver coming out. So the C is out of the board toward you. Do you understand what I'm saying?
No. Yeah.
And the cross product is always perpendicular to the A and the B. You notice if it's sticking out, that's perpendicular to A. It's sticking out, it's perpendicular to B. It tells you the direction of the plane in which A and B are located. So if you had A and B located in some weird plane like that, you can be sure that the normal to the plane is given by the cross product of A crossed into B. Or B crossed into A, that'd be in the opposite direction, but perpendicular to the plane containing both A and B. Do you understand what I said? And so here, basically, I have a current vector down, and I have a B field in, and so if I take the current vector and cross it into, which direction would a right-hand screw go? It would go in that direction. So that's the right-hand screw rule, I guess. You understand what I just said? Don't make a mistake on that, because that goes way back to what we studied at the very beginning.
Oh, no, we're trying it.
Are you using your left hand again?
No, I swear to God, that's the right one.
Doing this.
You gotta use the right hand.
One
And yes, you can use that sort of thing too. I usually like to think of the right hand screwed, and so I can't put all three right. They call it the right hand screw rule. And not the left hand. No left hand. Because then you will get negative signs, I suppose. Now, that's a simple case. Oh, and the other thing is that isn't quite true, because you find, there's an L in here. In other words, you get the L in this case is infinite. So basically, because this is an infinite current and that's an infinite current, yeah, you expect an infinite force. So they don't talk about the force, they talk about the force per unit length. How many newtons per meter are on this wire? And if this wire is 17 meters long, well, it's 17 times that number. So this is really the number that you want to get, because these things are infinite. That's the reason. Now, if you want to deal with a finite one, again, the mother might be, because the B field is so simple for this thing, I1 dl1, like that, and the B field going down is 1 over distance and all that. But instead of placing an infinitely long wire co-parallel, what if I placed the wire in and out? Like this. What would that do? It's infinite. You got a current C2, I2 on it. But what kind of a force would be on this guy due to the B field of mother? Huh? What direction is that current in and out of the board? It's in the X direction. What direction is the B field? It's in the X direction, right? What's the cross product between two co-parallel vectors? It's 0. 0, right? It's the sine of the angle between the two. The sine of an angle of 0 is 0. So basically, there would be no force on this infinite wire here. You understand what I'm saying? And that comes very fundamentally from that guy right there. The cross product of two co-parallel things, vectors, is 0, automatically. Don't have to even think about it. No right hand or anything. Yeah, okay. Now, of course, then I could ask questions like, oh, it's neither this way nor that way, but it's coming in at an angle like that, infinite like that. And what the heck's going on there? Well, then what you have to do is break this current up into one which is parallel and one which is perpendicular. The one that's perpendicular to the board gives you nothing, and the one that is parallel is the one that would give you this sort of a formulation. But that current, if you had, let's say, 1 ampere flowing on here, this looks more like 1 ampere times maybe sine or cosine of the angle, all right? You understand what I'm saying? So only part of that current counts. So you wouldn't stick the current I2, 1 ampere, you would stick a lesser current, maybe like I2 cosine of the angle between here and there and stuff like that. Do you understand what I'm saying? See, in other words, you can play all these games. If you just understand what you're doing, you can play all those games. Then the kind I might give in class might be something like this. So let's say there's a current I2, DL2, and then continuing on. I might actually name them like, segment 1, segment 2, segment 3, and segment 4. So what you would do is divide, the old Caesar's technique, divide and conquer. So you do this one first, and you would get the force on this wire here. Well, that one is co-parallel with this, so you know that the force is going to be attractive. There's going to be a force F1 on that guy, right? Like that, right? And how much of a force? Well, basically, you'll take this formula and you'll say, the L, he's half a meter long. So then you put a half over here. Do you understand what I'm saying? And you get the actual force. And then you say, maybe I should have called this number 2. A little further away is this fellow here. Now, that means that the B field is going down as a hyperbola. It's weaker here than, now the current is the same, of course. The current is the same, I2. But the B field is weaker. So if the B field is weaker, even though the current is the same, I'll bet any money that the force is going to be weaker. And it's going to be, as a matter of fact, let's see, this is anti-parallel, right? This is going like this is going, it's going to be in that direction. And so this would be F3, and F3 is, let's say, small, and F1 is big. Let's just think about it that way. And then how about these two? Well, this current is the same as that current. And one is in one direction, one is in the opposite direction. But the B field here, and here, and here, and here, and here, is in. So as a matter of fact, the force on this one is maybe going to be up, and the force on this one is going to be down. But the B field here is strong and getting weaker, and you integrate the whole, how much force per unit length is here, less here, less here. You integrate that, and then you do the same thing here, and you find, by George, it's just that integral is exactly the same integral, except one is pointing down, one is pointing up. So F2 and F4 are equal to one another, and they don't, in other words, I guess what I'm saying is, this little, if you let it just sit there, this little guy, this little second circuit would not want to scoot up or down parallel to this, because the two forces up and down cancel one another. But the thing will want to suck in like that, because this force is bigger than that force. So if you let it go, it would go that way. Understand what I'm saying? Okay, so things like that. And then you can make it more complicated. I mean, complicated mathematically. I could say, oh no, my circuit's like that. I don't have three sides. This one is the same as that one is the same as that. How about this one? Oh, now you got to write the equation of this slope line and all that stuff. That's mathematics. But if you think about that's an evening. Think about it. I mean, I could give you that problem. Let's see. Pretty much talked about. Oh, there's another one. There's another one. What time is it? Yeah, I got time. Here's one that's kind of strange. Let's say this goes to infinity, and I have some current coming in, I1, DL1. And then what I do is I have a bar across. So the current is coming down here and then going back there. So this is still the I1. Well, let's just write it as I1. So many amperes, and so many amperes, and so many amperes, I1. All right? Now, what I want you to think about is, okay, if I look at this as being the zero on this axis, the Z or whatever you want to call that, I can think of the case in my library of where I have an infinitely long wire and I'm off to the side of its end. So basically this wire is this wire, and I'm talking about the B field off its end. It's strong here and getting weaker and weaker as 1 over the distance, right? And now that's not infinite, it's semi-infinite. But that's okay, because I can divide the infinite guy by 2, because I only got half the current. Do you understand what I'm saying? Okay, so the B field, and if I have this current in this direction, then the B field is out, huh? It's something like that. And then the same thing here. This is off the center, off this. And so you would find that its B field gets weaker and weaker. So the B field is actually along here is this kind of a thing plus this kind of a thing and out of the board, right? That's the B field, like that. Do you understand what I said? That's how you get the B field due to this current and this current. And the continuity of the current is caused by the current flowing through this short circuit or whatever you want to call it. Now, what I want to do is I want to get a force. A force. That means I need a second circuit. Well, the second circuit is actually this guy right here. We should even do it in color. This is C1, and this is C2. So in other words, the second circuit is actually part of the first circuit. Kind of interesting. Now, why is that interesting? Because if you then take the current that's flowing in the second circuit, that's this current, that's that current, and you cross it into this B field, let's see, down and cross it into something coming out, oh, there's a force on that, on this second circuit, like that, right? This would be the force on number 2, or whatever you want to call it. Do you understand what I said? Now, next step is, well, there's a force. What if I have, with these joints right here, a little explosive charge that opens it up and makes this thing, instead of a short circuit, sort of like a pellet. I mean, it's free to move. Well, that's the force that's going to make it move. And this is basically the background behind the fundamentals. All the details are much more complicated, of a rail gun, what they call a rail gun, an electromagnetic gun. This is the bullet. Now, it turns out there are some problems associated with it, but basically a railgun can create much more momentum for a mass than a chemical explosion can, or like a regular gun. This guy can really scoot. And the problem is that the minute he does scoot, then this current has, I mean, he's no longer here, he scoots off there, and there's no longer any place for this current to go. And that means that what was a loop, and what does loop have? Inductance. The inductance, suddenly the current goes to 0, and you know that changing current instantly in an inductor is a terrible thing. I mean, you can't do it. It's kind of like stopping a 100-ton locomotive in 1 inch. You can't, it's very difficult. So there are problems associated with this, but they've solved those kinds of problems. That's more a circuit kind of problem. But that's a rail gun. And what does it depend on? Ampere's force law. And of course, Biot-Savart. And this is a strange one where the second circuit is really part of the first circuit, for at least the first moments. Okay? So there's all kind of nifty things you can do with this stuff, if you want to. And when I was a student, it seemed as though, well, I remember, well, in that business of opening a coil, opening a loop with a current flowing in it was very demonstrated to me, very, how would you say, in a shocking way. I remember I was working at a bench. This is when I was, I don't know, junior in college. I was working at a bench. The bench was stupidly designed, and we were using high currents. I mean, there were, and so we had a single knife switch. Do you know what I mean by a single knife switch? In other words, it's just a pivoted kind of copper thing with a handle on it, and it would grab here or grab there. In other words, it was closed and now it was open, right? And basically that's the way it was. You opened it by shoving it, okay? And it had current flowing through it, like a lot of amperes. And I opened the thing, and guess what? Current doesn't want to stop. So basically, instead of stopping, a big arc formed across there and seared I got burned badly right here, right across here, because that thing, it should have opened like that. Then the arc would be over there and I'd be over here. But no, they designed it that way. Either that or I don't know, maybe I made the circuit wrong. But anyway, it taught me very quickly. The professor says you learned a good lesson. You do not stop current in an inductor. And that's what we're talking about here. Okay, I guess it's time to leave. And next time I'll talk about Ampere's second law, like his circuitous law. All right.